All right, so like I stated last week, in the final kind of video for the week, where I just kind of like introduced these properties, when we talk about properties of covalent substances, they are directly related to the strengths of the IMFs, the intermolecular forces, not the bonds. And I'll show you a simulation in a little bit that kind of lays this out for us. So again, in ionic compounds, the properties were determined by the strength of the lattice energy or the bonds, the energy of the bonds that holds the ions together in whatever ratio they exist in. In covalent compounds, the properties are determined by the amount of energy that's holding each molecule to the next molecule. And those are your intermolecular forces, whether they be London dispersion forces or hydrogen bonds or dipole-dipole or even ion dipole. But those forces are definitely not as strong as those intramolecular bonds. And for that reason, you'll see that covalent compounds tend to have different properties than ionics, and their properties are related to the lower strength that needs to be affected. Okay, so first of all, covalent compounds have relatively low melting and boiling points. So if you think about something like water, for example, when water melts, it melts at 0 degrees Celsius. That's very low. And it boils at 100, okay? And the difference between this and those ionic substances, again, is that when water melts, if it's an ice cube, when it's melting, instead of separating the H's from the O's, that'd be more like an ionic substance melting. It would be separating the atoms from each other. And when water melts from an ice cube, all we're doing is separating one H2O from the other H2O. So originally they're held together with hydrogen bonds as well as LDF and those dipole-dipoles. Those are holding each molecule together. So as it melts, we're basically just kind of like separating or moving those things, those molecules away from each other. And that doesn't require a lot of energy because all we have to do is break the intermolecular forces. We're not separating the hydrogens from the oxygens, okay? So we're not affecting the bonds. So instead, we're affecting only intermolecular forces to separate the molecules. And again, since intermolecular forces are relatively weak, they don't have as much energy as an intramolecular force or a bond. As a result of that, it doesn't take as much energy to do that. So we're going to see lower melting and boiling points. And again, with ionic substances, we said they had high melting and boiling points because in order to melt or boil an ionic substance, you have to break apart the lattice by disrupting the lattice energy. And there's a decent amount of lattice energy between a positive and a negative ion. In this case, because we're not changing how things are bonded, the shared electrons are still being shared, so we're not changing that. We're changing how attracted each molecule is to another molecule. And because of that, we don't need to put in as much energy to make that happen. Covalent compounds tend to be soft if they are solids, and that's because, again, it's easy to separate those intermolecular forces, break apart those intermolecular forces. They're not going to be brittle. They're able to change shapes because intermolecular forces are more flexible. So if you remember back to ionic substances, we talked about the lattice and how when you hit it, it shatters because the ions will realign, and now you would end up with a negative side and a negative side. And when you have two negatives and two negatives together, a positive and a positive, so those ions are shifted and now they're not arranged accordingly like they were before, that's what causes them to shatter. However, with covalent compounds, if I push on it or hit it, all I'm going to do is kind of like shift where the molecules are located. And because those molecules are held together by intermolecular forces, it's not a huge deal because intermolecular forces can exist over, different ranges and different distances and different kind of locations. So as the molecules rearrange, the intermolecular forces might rearrange a little bit, but they'll still exist. So as a result, we're not going to get this brittleness that we saw in ionic substances. Instead, we get soft solids. Now, with that said, most covalent things are going to be liquids or gases at room temperature, but there are some solid covalent compounds at room temperature, such as wax. Wax is a covalent compound. Any type of wax is a covalent compound, and those are very soft. If you think about wax compared to like salt, you can see that they're very different from each other, even though both of them are solids at room temperature. And you can also think about the melting point. Like it's really easy to melt wax. It's not really easy to melt salt. So that kind of leads back into the first property. Covalent compounds are never going to be conductive. And if you recall with ionic substances, we talked about the property of conductivity being in existence when ions are able to move or charges are able to move. And because the charges or the ions are unable to move in covalent compounds because there is no existence of charges or ions, that means that they're not going to be conductive regardless of the state of matter. If it's a liquid, it's not going to be conductive. If it's a gas, it's not going to be conductive. If it's melted, it's not going to be conductive. If it's a solid, it's not going to be conductive. If I put it in water and dissolve it, it's not going to be conductive. Again, we don't have ions or charges that are able to move because these are covalent compounds that are sharing electrons. They're not ionic compounds. In ionic compounds, we had ions and charges that once we put them under certain conditions, whether we melt them or put them in solution, the ions are now free to move around, and that allows the conductivity to exist. Covalent compounds don't have ions in the first place, so there's no charges that are able to move. It's not that they don't have electrons, they very much do. It's that those electrons are held between the atoms that they are being shared between. They're attracted to both of those atoms. Those electrons aren't going to leave that attraction. So covalent compounds do not have conductivity no matter what you do to them, okay? And some of you might be thinking like, but wait, if we're talking about water, like why is it so dangerous to have, say, electrical things, like say you can't dry your hair while you're sitting in the bathtub, because people talk about water being able to conduct electricity and you can get electrocuted. But in all honesty, it's not because of the water itself, it's because of the impurity of the ions that are contained within the water. In our water that comes out of the tap, there's a lot of impurities. It's not pure H2O. So there's a lot of ions and a lot of substances that are contained within that water. And it's those impurities that actually allow for the conduction. So it's really the ionic substances and the metals that are in our water that allow for the conduction. It is not the water itself. If you had straight up water, just pure H2O, it wouldn't conduct electricity because there'd be no available charges to move. The last property of covalent compounds is a little bit tricky, and that's solubility. So there's two groups of covalent compounds, remember? There's polar covalent compounds and nonpolar covalent compounds, okay? So that's going to play a role when we talk about solubility. And the general rule for solubility of covalent compounds we say is like dissolves like. And let me explain what I mean by that. If I have a polar substance and another polar substance, they can be dissolved into each other. So water, for example, can dissolve all sorts of polar things, okay? Water cannot dissolve nonpolar things such as oils or fats. And again, that should kind of like ring a bell, like, oh yeah, oil and water don't mix. If I take oil and water and put it together, they're not going to mix. Nothing's going to dissolve into anything else. They're going to constantly separate. And that's because there's nothing that's attracting the water molecule or water molecules to the oil molecules, okay? So in order for things to be soluble, essentially what we need to do is we need to make an attraction between substance A, call it the solvent, the thing that's doing the dissolving, attraction between the particles of substance A and to the particles of substance B. So if substance A is water, and water is very polar, we want water to be attracted to whatever the solute is, substance B. Let's call that water or oil in this case. So substance A is polar water, substance B is nonpolar oil. Well, nonpolar oil molecules are held together with London dispersion forces, and they are okay being held together with London dispersion forces to each other. Water molecules are held together with polar dipole forces, hydrogen bonding, and London dispersion forces, which we know is pretty strong. So on one side in substance B, we've got these really weak, relatively weak LDF forces. Water's being held together with really strong LDF dipole hydrogen bonding forces. So there's not really a reason that the water would start attracting the molecules of oil, because the water is held together with such strong bonds, or such strong attractions, such strong intermolecular attractions, that there's nothing else, there's no reason why it would attract water or oil particles, because it's not going to be as strong of an attraction, okay? So because these water particles or water molecules are held together so tightly with those really strong intermolecular forces, there's nothing really promoting them to attract oil particles, all right? However, water will dissolve other polar things, okay, because there's positive and negative ends on other polar things. So if I took another polar substance, in alcohol, for example, say ethyl alcohol or ethanol or any sort of alcohol, and I mix it with water, it will dissolve. And that's because the polarity of both of the substances create those positive and negative ends that then can be attracted to each other. If I took oil and put alcohol in it, it wouldn't mix, because alcohol is a polar substance. Oil is nonpolar. They're not going to mix each other. So nonpolar things don't dissolve in water. Nonpolar things do not dissolve in polar things. Polar things will dissolve in polar things. Nonpolar things will dissolve in nonpolar things, okay? And the reason is the nonpolar substances have no attraction to the polar water molecule. The polar water molecules are attracted to each other really strongly. They don't attract to those nonpolar substances at all because there's no positive or negative things. But nonpolar can dissolve in other nonpolar. It's all about the relative strength of LDF. So if I have an oil substance that's nonpolar and it's held together with LDFs, and I give it something else that can create stronger LDFs, that other substance can cause the dissolving of a nonpolar thing. So it's all about maximizing those intermolecular forces, okay? And again, a really good example of this is oil and water do not mix. Oil is nonpolar, water is polar. They're not going to mix, okay? Polar molecules can dissolve in water because they create that Coulombic attraction between charges. The attraction between positive and negative charges, even if they are temporary positive and negative charges, those dipoles are positive and negative. Therefore, they will create an attraction to other positive and negative things. And this is also the reason that ionic substances will dissolve into polar substances, because polar substances have a partially positive, partially negative end, and they attract the ions of the ionic substance, okay? So that's the other reason that polar substances can dissolve ionic substances. In polar substances, you've got positive and negative ends. In nonpolar substances, you don't have positive and negative ends. If you took salt and you put it into oil, it would not dissolve, okay? Because there's nothing to pull the NAs and the Cls apart from each other, and that's what's needed to dissolve an ionic substance like salt. There's nothing to pull them away because nonpolar substances don't have a positive and negative end. But you can take salt and put it in water and it will dissolve because water has a positive end and a negative end that can then attract the ions, all right? The next slide I will go through will show you an animation that kind of goes through the difference between sugar and salt when they dissolve and how it looks different. And here's a little joke that I'll leave you with.